alkanes. So guys, don't worry. This crash course will be the shortest crash course you will ever watch. Diba? So again, for alkanes, we will discuss the structural features and properties. Check. Chemical reactivity. Check. Sources and uses. Check. And finally, class, conformers or conformational isomers are specific or unique to our saturated hydrocarbons, alkane. That's why we also need to somehow briefly discuss the conformations of our representative alkanes and cycloalkanes, particularly or specifically your cyclohexane. And with that being said, class, let's start our discussion on our structural features and properties. Ayan, so for our alkanes, it has several applications. So firstly, it is our main fuel component. So class, particularly in our natural gas, it is mostly composed of methane. So aside from that, it also serves as our solvent in the laboratory. Remember, diba? Your hexane particularly is a type of alkane. And usually this is used in column chromatography for fractionation and purification of our samples. Next, of course, we also use it in our lubricating, diba? For lubricants in our engines. Aside from that, ayan, it also serves as an anesthetics in our clinical field. And finally, for the cosmetic industry, of course, we use it in our formation of your waxes. And for pharmaceutical, of course, it's also used as carriers or particularly starting materials in order to synthesize drugs. As again, your alkanes is one of our hydrocarbons. For your hydrocarbons, we can actually categorize it based on two types. Saturated, meaning it has no double bonds, or triple bonds. So for saturated, we have your open chain, that's just your alkanes, and your cyclic, that's your cycloalkanes. For unsaturated, on the other hand, so that is your alkenes, and additionally, alkynes. We also have your open chain alkenes and alkynes, and their cyclic counterpart, your cycloalkenes or aromatic compounds. Okay, class, I hope it's clear again. Your alkanes, alkenes, and alkynes, including your aromatics, they are just chains of hydrocarbons. But again, for our discussion here, let's just focus on your alkenes. So in terms of its structural feature, alkenes are the simplest class of hydrocarbons. And remember, from our discussion of your functional group, it is considered as aliphatic. So for your alkenes, we have its normal structure, the straight chain. Remember our discussion class on your isomerism, diba? This is our normal structure of your alkenes. So here, we are in your continuous unbranched chain. So for instance, we have your butane, a 4-carbon linear chain of your alkane, and of course, hexane, this is a 6-carbon compound. So if we have straight chain again class, we also have branching, the constitutional isomerism. That is a particular feature of your alkane functional group. Now, let's see. Ayan, for branched alkanes, of course, we have your examples here. For butane, it's constitutional isomer, isobutane. Of course, for your hexane, you can see it's constitutional or structural isomer, your 2-methyl pentane. So class, for our types here, your straight chain and branched alkanes, they only adapt the similar general formula. Okay, so again, that's C sub n, H2 sub n plus 2. But for your cyclic ring structure of your alkenes counterpart, of course, your general formula now will change. As you can see, this is just simply C sub n, H2 sub n. Ayan, so again class, for cycloalkanes, that's your saturated hydrocarbons, wherein you will form a ring structure. For instance, we have cyclopropane, a cycloalkane with 3 carbons, and cyclohexane, a cycloalkane that has 6 carbons. So remember class, for our structural visualization, we use now your line angle structure. Okay, so class, we have a did you know segment here for our discussion. Did you know that methane is actually over 25 times more effective at trapping heat than your carbon dioxide? So usually, your methane are produced naturally by wetlands and in large amounts by your organisms, like your ruminant animals, for instance, your cow. So methane plays a major role in global warming despite being less abundant than carbon dioxide. O C-class, greenhouse gas pala si methane. Its potency as a greenhouse gas makes it a key target in climate change mitigation strategies. Class, again, our greenhouse gases involve carbon dioxide, methane, and nitrous oxide. And in particular, your methane accounts for about 16% of all greenhouse gas emissions. Ayan, so remember class, methane is a component of our natural gas. Okay, so class, let's now proceed with our discussion with our sample problem. So remember, your alkenes have distinct structural or constitutional isomerism. So for our sample problem here, check. For our C6H14, particularly hexane, we now have 5 isomers. So class, for our sample problems, draw all isomers for our C6H14 alkane. So of course, given the class yung first one, the straight chain is your hexane compound. Alright, so for the 4 remaining branched alkane or branched hexane, please try answering the sample problem. So you can pause the video in order to answer our sample problem. But I will now discuss the 4 remaining branched isomer. First one, here we have your class, this is 2-methylpentane. You can check its structure or nomenclature based on our discussion on IUPAC naming. If we have 2-methylpentane, we also have 3-methylpentane. So for the last two, of course, this is more branched. We have 2,3-dimethylbutane. So for this one, and for this one, 2,2-dimethylbutane. Okay, class, so very straightforward lang yan, sir. Do we need to memorize the other alkane isomers? Class, no need. It's just easier to deduce. Again, for our sample problem, as you can see here, hexane, C6H14 for its molecular formula has 5 isomers. Okay, so class, again, that's for our branched and normal chain or straight chain alkanes. For your cycloalkanes, remember, of course, we have this particular feature. Because of its cyclic ring structure, we will now introduce the concept of angle strain. So this is particularly evident for our cyclopropane because of its sterically hindered cyclic ring structure. So for angle strain, this increase in energy when tetrahedral bond angles deviate from our optimum angle of 109.5 degrees. So remember class, our discussion of our hybridization for your tetrahedral carbon. Class, remember, for cyclopropane, sterically hindered because of your 3-carbon compound forming a cyclic ring. So for cyclopropane class, it adapts around 60 degrees of its bond angles. Okay? So again, 60 degrees. For your cyclobutane, that's around 90 degrees. Okay? And lastly, for cyclopentane, so class, this is the nearest. Okay? Its angle is the nearest angle with our optimum angle of 109.5. So that's about 108 degrees. So don't forget, for cyclopropane 60, cyclobutane 90, and cyclopentane 108 degrees. Class, again, for our cyclic alkanes, we have angle strain because of the deviation from our optimum angle of 109.5. Alright, so class, for our next discussion, this is with our classification of your hydrocarbons with our alkanes structural property. So for our classification, we actually have 4. Firstly, for your primary, when we say primary, your carbon is directly attached to a single or R group, a alkyl or an alkyl substituent. Okay? So remember that. For your secondary, or C, we now have 2 different R groups or carbon-containing substituent. Okay? So for tertiary class, obviously, 3 different carbon groups. And for quaternary, ayan, your carbon atom is now bonded to 4 different functional groups. So class, this is in terms of our central carbon atom. Primary, secondary, tertiary, quaternary. For the symbol R group class, again, this is used here and throughout our organic chemistry discussion. So they represent a generalized organic group. So it can be your methyl, ethyl, or propyl. Okay? So again, these are routinely used, your primary, secondary, tertiary, and quaternary. Ayan, for our hydrogen naman, we can also categorize it as primary, secondary, and tertiary. And this one is in terms of the connection of your carbon with our different alkyl substituent. Now let's check. For primary hydrogens, they are connected to the carbon that is bonded only with one R group. Clear? For secondary, or C, your hydrogens are secondary if the carbon where they are attached is also bonded to 2 different R groups. Ayan. And lastly, tertiary, of course, this one, your carbon in which your hydrogen is attached to is also bonded to 3 different R groups. Class, there's no such thing as a quaternary hydrogen because for your quaternary structure, your hydrocarbons will now adopt this structure. So wala na tayong hydrogen in your structure. That's why we only have primary, secondary, and tertiary hydrogens. Okay, so please remember that again for our alkanes. Okay, so class, let's now move forward with our discussion of the physical properties of alkanes. Let's discuss this briefly. For the state of your alkanes, this one is actually dependent on the number of your carbons in its skeleton. Okay, so remember, alkanes can exhibit a range of different physical properties. So particularly class, here we will discuss boiling point, melting point, their distinct solubility, and of course, the influence ng chain length and branching with this physical properties. Ayan, very important that you understand the general trend. Going back, for your hydrocarbon chain of your alkanes, that is around C1 to C4, they exist as gas. For instance, methane to butane, they are components of our gases. Ayan. Next, for your alkanes that have C5 to C17, they are usually liquids. So for instance, pentane to heptadecane, they are liquids. And usually class, they are used for, or they are used as solvent. And lastly, for your alkanes that have 18 carbons or more, they are solids. So very strong na kasi class ang intermolecular forces of attractions. For instance, you have octadecane. Okay, so next. Now we have your other. So usually class, alkanes in general, they are odorless. Okay? So of course, they have characteristic solvent smell lang for our distinct types of alkanes. For instance, class, this one is experimentally determined. Propane and hexane, they have somehow a distinct smell. For propane, faint smell. For hexane, ayan, the typical solvent smell. Okay, class, next we have your boiling point. Sir, do we have a general trend here? Yes, as you increase your chain length, of course, your boiling point will also increase because of the increase in your intermolecular forces of attraction. Alright? Of course, additionally, when you increase your branching, so of course, relatively class, tightly packed na yung structure na alkanes natin. And that's why it will result to the decrease of your boiling point. C, for your butane, pentane, hexane, and octane, remember, this is with their increasing chain length. And as you can see with their boiling point, of course, there are, in terms of their relationship, they are directly proportional. With your butane, of course, having the lowest boiling point and lowest carbon chain length, and octane having the highest boiling point and carbon chain length. Sir, how about for the melting point? Class, here we don't have that specific trend. So we have irregular increase because we need now to consider the symmetry of your alkanes. So in particular, your more symmetrical alkanes will melt higher because, of course, of the intermolecular forces of attractions in our structure. So remember class, your melting point and boiling point, they are different, ha? BP is the temp at which your substance becomes a gas. So, diba, from Phychem, you discussed this. For melting point, this is the temperature at which a substance becomes a liquid. So that's our definition of your boiling point and melting point. So class, of course, I hope you are ready with two properties of our, well, in general, organic compounds. And lastly, with their solubility, of course, these are just chains of hydrocarbons. So they are relatively, class, insoluble in water because they are nonpolar compounds. And of course, we have they are soluble in nonpolar solvents. For instance, hexane dissolves in ether, but it's insoluble in water. Okay, so class, additionally, for the physical properties, let's now discuss, again, the specific relationship of your structure with our boiling point. See, again, this one is our example from our previous slides. And remember, as you increase the number of carbon in our hydrocarbon chain, of course, you will also increase the IMFA from your GenChem, and eventually, we will now have boiling point because of the large surface area that is site for our IMFA. Class, this is just the same example that we discussed from our previous slides. Class, again, increasing, they have direct relationship. Next. Ayan, in terms of your melting point, in terms of your boiling point again, with your branching naman. So here, if you have branching or if you have a compound that is highly branched, ang tendency is to decrease the boiling point. Let's see again our summary. Class, remember, the larger the surface area of your compounds with the same molecular weight. Again, we can only compare your compounds with the same molecular weight. For those compounds, the larger the surface area, SA, the higher the boiling point. So in turn, if you have a compact structure, remember class, this compound will have a relatively shorter or smaller surface area. That's why for neopentane, a compact isomer of your N-pentane, it has a low boiling point compared to your N-pentane that is a linear form, thus high ang or large ang surface area niya. Again, class, I would like to reiterate, for your chain length, as you increase it, it will also increase your surface area, and in turn, your boiling point will also increase due to higher IMFA or intermolecular forces of attraction. Now, for our slide here, again, as a summary for branching, as you increase the branching, you will now lower the surface area, and in turn, it will lead to a weaker IMFA. And finally, class, the result is a lower boiling point. So, as a result, or as a summary, we have inverse relationship for the branching. Increased branching, decrease boiling point. For the chain length, direct, you have the increase in the number of carbons, then your boiling point will also increase. Okay, so class, next topic that we will discuss is on the constitutional isomerism. Remember, we already discussed this briefly on our discussion on stereochemistry. Again, this type of isomerism, we also call it your structural isomerism. So of course, this is because of the various ways of how carbon atoms are arranged in our structure to form your straight or branched chain. Class, diba, as we discussed, as your number of carbon atoms increases, also the number of your possible isomers will increase significantly, actually exponentially pa nga. Okay, so again, for constitutional isomerism, recall, similar molecular formula, but they have the difference in their structural arrangement of their atoms. So because of that, they also have varying physical and chemical properties, such as your boiling point, melting point, and density. And class, remember, diba, I emphasize this in your stereochem discussion, we only observe, firstly, your constitutional isomerism, starting with butane, a 4-carbon alkane. Class, remember, for butane, we have your straight chain butane and your branched alkane isobutane. So usually from our previous slides, which has a lower boiling point. Diba, because of the branching, you have a smaller surface area, and then it will result to a weaker IMFA compared to butane, and thus, much lower po ang boiling point ng branched isomer natin. So that's the general rule. The isomer with more branching typically has a lower boiling point due to your decreased surface area. Alright? So class, again, I have discussed this. Sa butane, it has 2 isomers. One is the normal straight chain, your N-butane, sorry, and one is your isobutane. Another one, si pentane, diba? From our discussions on our intro, how many isomers does pentane have? Again, we have 3 isomers here. First one is the straight chain pentane, and of course, we have your isopentane, your branched pentane, and the highly branched pentane, ayan, your quaternary carbon in our structure of your neopentane. Let's discuss the physical properties of these 3 isomers of your pentane. Let's check with our summary here. So class, this one is also available in your manual. See, again, we discussed the type, the skeletal structure, and the space filling model. Recall, highly branched C neopentane, that's why it's also highly packed or highly compact ang structure ni neopentane. So in terms of the surface area, as you can see class, in the space filling model, N-pentane has the highest surface area. Next is isopentane, as you can see. And then last, very compact in neopentane, thus small ang surface area niya. So in terms of your intermolecular forces, class, your surface area and IMFA, they are directly related. As you increase the surface area, your IMFA also increases. That's why similar trend lang po. Okay? And pentane has a higher IMFA compared to your isopentane, and isopentane IMFA than neopentane. Alright, for boiling point, we discussed this again, class. Your surface area, IMFA, and boiling point, they have direct relationship. Ayan. So class, that's it for our physical properties. Our next topic will be about the chemical reactivity of your alkanes. Remember class, relatively unreactive po ang alkanes natin due to the nonpolar saturated C2C and hydrocarbon single bonds. So for your alkanes, we actually have 3 distinct reactivity: combustion, halogenation, and cracking. So we will discuss this in detail here in our discussion. Okay, so class, remember, for combustion, our conditions require oxygen and heat. For halogenation, OC, this is a light or heat-induced reaction. And for cracking, usually this is extreme temperature or through extreme pressure. So class, due to the unreactivity of your alkanes, we need to include extreme conditions in order to proceed with our 3 different reactions. So don't worry, we will discuss the specifics of our combustion, halogenation, and cracking. So here for our general reaction, no need to memorize, okay? So again, for the products, check. For combustion, actually, we have the term complete and incomplete. So it's based on your reagent or the conditions where your alkanes will be proceeding. For halogenation, class, usually we will form halide or hydrogen halide in particular using your free radical halogenation. For cracking, class, usually this is used for our petrochemical industry. All right. So again, for combustion, that's our major energy source, such as coming from your fuels. For halogenation, so usually for synthesis in your pharmaceutical, and for cracking, class, this is our main source in order to produce useful products. All right. So here are our distinct or specific discussions on our 3 different types of the reactions for our alkanes. Again, for complete, it depends on our oxygen supply. So between complete and incomplete, ayan, of course, you can see if we have available oxygen supply, or sufficient complete combustion will occur. However, for those conditions that has limited oxygen supply, of course, incomplete combustion will be occurring. See class, for the energy release, we have high energy release for complete combustion because of course, we will totally combust our methane or carbon-containing alkanes. For incomplete class, ayan, very straightforward lang naman, lower. And of course, for the reaction of class, take note of this. For complete, the products include carbon dioxide and water. But for incomplete, usually carbon monoxide, or remember, that's a toxic gas or soot. Basically, that's just your carbon atom. All right? So in terms of their efficiency, of course, that's related to your energy release. Because your complete combustion releases high energy, it's efficient compared to your incomplete combustion. And class, remember, harmful unlimited combustion because of the production of carbon monoxide. Remember, that's a toxic, okay? Toxic gas, while your soot is a pollutant. All right, so class, in order to visualize your incomplete and complete combustion, ayan. In terms of our experiment here, incomplete combustion, usually yellow yung flame na napaproduce. For complete, of course, high in energy, o diba, usually associated yan with the production of your blue, roaring, and extremely hot flame. Okay, so remember class, our main product for incomplete combustion, either carbon monoxide or soot. Again, for incomplete, limited oxygen supply. For complete combustion, again, we have a sufficient oxygen supply. Class, don't worry, we are already done, or we are almost done with our discussion here. Ayan, for halogenation, of course, class, again, our reaction here is through free radical substitution. Because of the unreactivity of your alkane, we need light or heat in order to proceed with our halogenation. So because of radical substitution, of course, we will form radical intermediate. So class, again, for our halogenation, this one occurs through three main stages. First one is initiation. So this one is induced by light, wherein we will produce your halogen radicals. So for instance, you have a diatomic chlorine, and then when we subject through light or heat, it will become, or it will be cleaved in order to form two radicals. And this will be our important products in order to proceed with our next step, the propagation step, wherein your radical will react with your new radical. So class, again, it's like a chain reaction. Because of the reactive, the reactive nature of your radicals, it will react with our alkanes. See, for our step 2, it will obstruct a proton coming from our typical alkane, or for this one, this is ethane. And because of that, check the product. We will form a new radical and the byproduct, HCl. So again, for the third step, this formed radical from your second step will then react again with our diatomic chlorine, and here is our final product supposedly, plus formation of your side product, chlorine radical. And plus, remember, propagation step will just be repeated, okay? So again, your steps 2 and 3 will be repeatedly done. Ayan, for our last step, termination is when your two radicals react to form a sigma bond. See class, here, your reactive radicals will then eventually react with each other to form our three main products. When your chlorine radicals react with each other, you will regenerate our original reactant. When your two alkyl radicals react with each other, class, check the product. It's an alkane with an increased carbon chain. All right? And for our very important product, this is our alkyl halide. When your alkyl and chlorine radicals react to form the alkyl halide. All right, so class, again, that's it for our halogenation. Remember, our halogenation reacts through radical substitution. So with that, let's go to our last discussion, the sources and uses of our alkanes. So let's watch this short animation.
In this video, you will learn how fractional distillation separates crude oil into useful fractions. Crude oil is the term used to describe unprocessed oil. That is oil that has been taken directly out of the ground, either on land or under the sea. It is an exceptionally valuable resource. It provides us with a great number of hydrocarbons, some of which are useful as fuels, and others are used in the manufacture of many different chemicals and even plastics.
Class, again, to start, industrially speaking, our sources of hydrocarbons are your crude oil. And our crude oil is fractionated through the process of fractional distillation. So this will be the focus of this video. Let's continue watching.
However, in the raw form as crude oil, it can be a viscous, dark-coloured tar-like consistency, and the different fractions of hydrocarbons must be separated by fractional distillation for them to be useful. Before we understand how fractional distillation works, we should be clear that crude oil is a mixture of hydrocarbons with different chain lengths, some being short molecules and some being very long. Intermolecular forces act between molecules, and the longer the molecule, the greater the intermolecular force. As you can see here, the small molecules have weaker intermolecular forces, and so will require less energy to break them apart and turn them into a gas.
Class, again, we discussed this on your physical properties of alkanes. So in order for you to understand fractional distillation, remember, the basis of fractionation or separation here is the differences on the boiling point of your several hydrocarbons or mixture of hydrocarbons. Diba? In terms of the chain length, as you increase the chain length of a certain hydrocarbon, you will also increase the surface area. So in turn, you will also increase the intermolecular forces of attraction. That's why you need more energy in order to break this IMFA. And as a result, you need to have a larger input of temperature. That's why, diba, we concluded, as you increase the chain length, your boiling point will also increase. So remember, for fractional distillation, our basis of separation is the boiling point differences. Okay.
They have a lower boiling point. The longer molecules have greater intermolecular forces. More energy is required, a higher temperature will be needed to evaporate these molecules. They have a higher boiling point. Now we understand how chain length is related to the boiling point of a molecule, let us look at how this method works. As you can see, crude oil is heated up to a high temperature outside of the fractionating column. The hot crude oil, now mostly in vapour form, is pumped into the column. The column has a heat gradient and is very hot at the bottom, going cooler as we move up to the top. Even at the very bottom of the column, where the temperature is still some long chain molecules with high boiling points begin to condense back into a liquid. These are collected at the bottom of the column.
Class, again, to emphasize, in your column that is used in fractional distillation, so usually this is through mass, okay? A mass column used in the industry. So you have a higher temperature at the bottom, and then as you go at the top, this temperature will decrease. That's why I said in the video, at the bottom, hotter temperature, at the top, cooler temperature. Okay.
The rest of the molecules start to rise up the column, making their way through bubble caps in each tray. The bubble caps slow down the rate of the rising vapour, and eventually the vapours get too cool, condense, and are collected as liquids in the trays. Small molecules have low boiling points, and so condense much higher in the column, where the temperature is cooler still. As you can see, hydrocarbons with similar boiling points are collected in the same tray, and this is why they are known as fractions. They are mixtures of hydrocarbons with similar boiling points. Each fraction has some important uses. Some examples of fractions are petrol, useful as a fuel for cars; naphtha, used in the manufacture of chemicals; kerosene as aircraft fuel; diesel oil, used as fuels for vans, cars and lorries; and bitumen, a mixture of large chain hydrocarbons used to lay roads. Now, at the end of this video, you should understand that crude oil is a mixture of important hydrocarbons, and that fractional distillation is the method used to separate crude oil into useful fractions with similar boiling points. You should understand that small chain molecules are collected at the top of the column since they have lower boiling points, and larger chain molecules are collected further down the column as these have higher boiling points.
Okay, so class, that's it for our fractional distillation. So for this one, let's translate this video in a more important visualization or diagram. Again, this is the process of your fractional distillation. So let's summarize the characteristics of your hydrocarbons at the top of your column. So remember, because they have low boiling point, low viscosity, and high flammability, they are easily converted to gas. So typically, these are your liquid petroleum gas, LPG, diba? And at the bottom, ayan, because we need higher temperature, we have your high boiling point. They are highly viscous, and they have low flammability. Okay, so again, your bitumen, we also call this your asphalto. So if you have seen how asphalt roads were made, initially they are in liquid state, and then upon some time it will become solid because again it has high boiling point. All right, so that's it for our fractional distillation. Now, as a supplementary discussion, let's also discuss how your petrol or petroleum and natural gas are naturally formed. So here is our diagram. So again, formation of your oil and natural gas takes over 1 million of years. Again, for instance, diba, around 300 to 400 million years ago, when your marine organisms died and they settled on your ocean floor, they are buried under layers of sediment and drag. As you can see in our second picture. So over time, heat, pressure, and other external factors will transform your marine organisms. Remember, they have organic material, and this will be converted into oil and gas. And this will be accumulated into your porous sedimentary rock layers. So these rocks and sediments will contribute to the pressure that will convert your organics to your oil and gas. And these deposits became trapped beneath your non-porous hard rock. Thereby, they are prevented from escaping, diba, hindi makaalis. And of course, at the present time, we use mainly drilling technologies in order to access these trapped fossil fuels, mainly for energy use. Class, remember, our fossil fuels reserve are now becoming depleted. That's why we need to find alternative energy source. Remember, we only have limited fossil fuel reserve. And it takes about 300 to 400 million years, around 300 to 400 million years pa before we again produce your fossil fuels. Okay, class, again, for the sources and uses, let's have a recap. For your natural gas, mainly we have methane, ethane, propane, mixture of short-chain hydrocarbons. On the other hand, for petrol or petroleum, this is produced or extracted through fractional distillation or cracking. This is the fragmentation of long-chain hydrocarbons to produce more useful smaller-chain alkanes. Okay, so again, ayan ang applications ng alkanes natin. Used in cooking or heating, as fuel source, as lubrication or lubricants in our engines, and of course, in the industry, we use your crude oil in order to produce or fractionate your several hydrocarbons. Again, don't forget the processes, class. For fractional distillation, basis of separation, the difference in the boiling point of your components. Usually, short chain, low boiling point, and then your long chain, high boiling point. Of course, we have the process of cracking. Again, this is the process where we break long chains of hydrocarbons into useful smaller alkanes such as this three. Okay, don't forget, class, your natural gas, they are mainly composed of your short chain hydrocarbons. And for applications, again, for your methane, propane, and butane, ayan, diba, we have your butane gas that we mainly use for the samgyup. Okay, for the samgyup experience. And additionally, your octane, or we also call it commonly as gasoline, it's also used for transportation fuel. And lastly, for industrial use, ayan, as solvents, lubricants, and precursor molecule for synthesis of chemical feedstock such as plastics, alcohols, and other organic compounds. All right, we are done with our discussion here. Alright, so class, our next topic for our discussion on alkanes will now be focused on conformation. So this will be our last topic. So this particular topic is very important for your alkanes because of their single-bonded carbon-to-carbon bonds. So due to that reason, we actually have free rotation in the structure of our saturated hydrocarbons. Class, again, free rotation is possible around our C single-bonded to another carbon. And here, different arrangement can actually result from our bond rotations. And because of that, we can actually produce or form molecules that have different arrangement. So we actually call them conformational isomers or simply, ayan, conformers. But remember, unlike your constitutional isomers that we can isolate in your solution, your conformers or your conformational isomers actually are impossible to be isolated. Sir, what's the reason? See, they interconvert too rapidly. So again, very impossible to isolate different conformers. Class, to visualize our free rotation that occurs for your CC single bond, check this visualization. Ayan, as you can see, the free rotation around our CC single bond. So remember, this is particularly unique for your alkanes because of its CC single bond. So in order to discuss your different conformations, actually, we will now use different models. But class, we already discussed this briefly on our previous discussion. So are you familiar with sawhorse versus your Newman projection? O, diba? As we have discussed previously, this is the tilted view of your organic compound. So here, very clear ang structure or the conformations that your organic compounds adopt. For our sawhorse and Newman projections, we have the two different conformations, staggered and eclipse. Okay? So relatively, staggered is more stable than eclipse. As you can see here kasi for eclipse, almost 0 degrees ang bond angle between your two substituents. Comparing it with your staggered, ayan, around 60 degrees apart ang angle ng two substituents natin. But to summarize again, as we have discussed, the viewpoint for sawhorse, it is tilted. As you can see here, it is an oblique angle at an angle in order to view clearly the staggered and eclipse conformation. For Newman class, again, this is an end-on view. So our front view here actually is your single carbon atom. And at the back, ayan, is another single carbon atom connected to your three different hydrogens. Remember, for the carbon atoms here, we actually assume that they are in the center in our apex, okay? For sawhorse, it is shown in zigzag. As you can see here, ayan, we have your single bonded here, carbon to carbon bonds. For your Newman, your dot structure here is actually this one, ayan, and for the circle structure, that is our rear carbon atoms. It's behind our dotted carbon atoms in front of our Newman projection. Or remember, for the bond display, much more clear ang perspective or the bonds shown in your sawhorse compared to your Newman because for Newman, class check the bonds radiate from your center to our different lines in order to visualize the substituents that are directly attached to our carbon. Our center, carbon. O, see again, that's the unique feature of your Newman projection. And finally, sir, what's the main use of these two different projections? For your sawhorse, more on 3D geometry in order to analyze the bond angles and of course, sterics class. For Newman, usually for conformations that we will discuss later, plus the steric strain. O class, check here. Much more easy to understand ang eclipse because you can really visualize that the two substituents are near, between or near from each other. Alright, so I hope it's clear. Again, remember the difference between your sawhorse and Newman projection. Or to add, here again is another set of info about the difference naman on our conformation staggered and eclipse. So earlier I had a sneak peek already with regards to their stability. So I teased you class that your staggered stable because around 60 degrees ang bond angle natin between your two substituents from your different carbons. On the other hand, for your eclipse, check around 0 degrees because they are actually almost near from each other. That's why, remember, your stability and energy are somehow related. If you are stable, meaning you are a low energy compound. And on the other hand, for a compound that is least stable or unstable, of course, it contains high energy because of the strain generated from your two nearby substituents. Clear with our first two feature. Next, with the bond position, again, 60 degrees so your bonds are maximally separated. Diba? For your eclipse class, again, as I have said earlier, they are somehow aligned or near with each other. That's why for your bond position, it is related to your torsional strain. Okay? So again, this strain is for staggered, minimal, but for eclipse, it is at maximum. Alright? Class, when we say torsional strain, remember, this is unique for your compounds, particularly alkanes that have CC single bond. Again, class, for torsional strain, it is a type of strain that arises due to electron repulsion in the structure of or in the electron clouds of our atoms or groups that are close to each other. Class, torsional strain is particularly evident for your eclipse conformation because, again, when they are eclipse, they are aligned and hence there will be an increased repulsion between your two nearby substituents. Again, torsional strain is particularly unique or exclusive to your conformations or conformational isomer. And here, class, we will going to discuss your conformers, particularly of our two representative alkanes, your ethane and butane. Okay? So class, let's discuss it in our next slide. Ayan. For your ethane, remember, I will introduce another type of angle. We call this your dihedral angle. So class, actually that's the angle that we are discussing earlier in our previous slide. So class, remember, this dihedral angle is simply the angle between your CH bonds in front and back of your carbons as viewed and on. So it is clearly visualized using your Newman projection. Okay? So again, here is a graph, okay? A potential energy graph for our ethane that shows the different conformation and their corresponding C, potential energy given their respective dihedral angle. Class, for your ethane, actually it can adopt 4 different dihedral angles. Let's check ha. We have your dihedral angle equal to 0, 60, 120, and ayan, the farthest dihedral angle for your CH bonds, 180. So with that, in terms of their energy, as you can see, your staggered conformation will have the lower energy compared to your eclipse. Actually, it's at maximum. Okay? So again, 12 kilojoule per mole energy difference between your staggered and eclipse. So class, this is your 12 kg per mole energy difference. Our reason there is due to the torsional strain, particularly in your eclipse. Okay? So again, this is the eclipsing of your bonds on neighboring carbon atoms. Alright? So that's it for our ethane. So remember, your bond rotation will now become more complex or becomes more complex for our larger alkanes. That's why we are just going to tackle our representative alkanes, ethane, and butane. So this is very important to study, class, because this is also a part of your board exam. Alright? So again, for your conformations, for eclipse, our reason to its maximum potential energy is your torsional strain. Remember, this is particular with your increase energy for eclipsing interactions. O, di ba? Class, relatively easy pa ang conformation discussion for ethane. So now, let's proceed to a more challenging alkanes, your butane, and the different conformers that it can adapt. So class, let's see. Alright, so class, again, for our next topic, let's now proceed with the conformations that our butane molecule adapts. So for butane, recall, we have a 4 carbon in its chain, and it is a linear alkane. Class, this graph shows the plot of your potential energy against our different dihedral angle that your butane molecule adapts. So particularly, each point along our x-axis, this represents the different dihedral angle starting from 0 until 360 degrees. Class, ayan, ang different conformers that our butane molecule adapts. Particularly, we have the eclipse conformations that have the highest energy. As you can see, it is at maximum. So what's the difference between these two eclipse structure? So remember, this one class is total eclipse, okay? So we will see the structure in your Newman projection for our total eclipse molecule. But for your butane, we will unlock new types of conformers. We have gauche and anti. And clearly class, anti is the conformers that has the lowest energy. Or see, our different Newman projection that your butane molecule can adapt. So starting at 0, we have your total eclipse conformation because check, ayan, your two methyl substituents are directly aligned. So this one will cause, again, the specific strain type is your torsional strain with added steric strain because your alkyl substituent, particularly the methyl, is actually a large substituent. Okay? Next dihedral angle. At 60 degrees, we reach your gauche conformation. So the metal groups now, class, are 60 degrees apart. So relatively, this will reduce your repulsion. So the energy will now become lower. Check quantitatively, that's around 0.9 kilocalorie per mole or around, 3.8 kilojoule. Clear with the first two dihedral angle. Now let's proceed with another eclipse conformer. For your 120 degrees bond angle, particularly dihedral angle, we have your eclipse conformation. Sir, it seems like your alkyl substituents here are far apart. Class, it is lower in energy than the totally eclipse form, but still relatively high with its 15 kilojoules because, ayan class, so they are still near or nearby from other substituent, particularly your hydrogen molecule. Eclipse pa rin yan compared to your staggered conformation of the gauche, particularly the gauche conformer. Next, for the anti, ayan, your 180 degree dihedral angle, your two methyl substituents are farthest, okay? They are farthest from each other. And because of that, this is the lowest energy arrangement for our butane molecule because the methyl groups again are opposite each other, thereby minimizing two different strains, torsional and steric, coming from your methyl substituents. Okay? Now, for your 240 and 300, we will actually just revisit the similar 120 and 60 degrees conformer. Again, they have similar energy profiles. And that's just also similar with our totally eclipse conformation because see, ayan, back to its original conformer, si butane natin. So class, overall, the butane molecule will prefer the anti-conformation because again, that's the most stable or that's the conformer with the lowest energy. Clear? Again, don't forget we have total eclipse and eclipse for your eclipse conformation. For staggered, we have two different subtypes. We have the gauche and also we have the anti that carries the very lowest energy arrangement of butane. Okay, so class, again, don't forget, for your butane, these are our different visualization or models. Diba, this is your dash wedge line structure, ball and stick model, and space filling model. Coming from your dash wedge line structure, much more evident ang steric strain natin. So for this particular conformer class, this is our totally eclipse conformation. Because again, as you can see, your substituents, our methyl substituents are aligned, okay, with each other. Alright, so I unlocked already the meaning of torsional strain. For steric strain class, again, this is the increased amount in energy resulting when atoms are forced too close to one another. Remember, for your torsional strain, that arises because of the free rotation around our CC single bond. Clear again with your butane molecule. Remember, we have four different conformers: total eclipse, gauche, and anti. Okay, so we are done with our two particular examples. So of course, in our discussion, we are also going to take a representative example for cycloalkane different configurations or conformations. So familiar with the chair and boat conformers, class, again, that's very prominent for our cyclohexane molecule. All right. Ayan. For cyclohexanes, actually, chair cyclohexanes are the most common conformer that your cyclohexane can adapt because it's a strain-free shape. Sir, what do you mean strain-free shape? Class, later we will see that your chair conformer has neither angle strain nor torsional strain that we have seen in your butane molecule because here we are assured that for your chair conformation, all CC single bonds are in tetrahedral angle of around 109.5. So technically class, our CH bonds are also in staggered conformation. Now, diba, check our visualization here. Cyclohexane again adopts a strain-free 3D shape that we call the chair conformation because it looks like a chair, and the boat conformer, it looks like a boat. So again class, here is our specific discussion of our chair conformations for your cyclohexane. In terms of your Newman projection, this is the structure of our cyclohexane molecule. But when we convert it to your chair conformation, now we will have two different positions: axial and equatorial. So class, this is your equatorial position, and this one, again, it's in your axis, so that's your axial conformation. Sir, which is more stable? Of course, always the equatorial. And because less stable is the axial, we actually favor the formation or our equatorial conformer. Remember, we have a ring flipping reaction that your chair conformer can participate to. All right, so again, shared cyclohexane has neither angle strain nor torsional strain because of our ideal tetrahedral angle of around 109.5. So this is derived from our sp3 hybridization, coming from our discussion on our hybridization properties of your organic compounds. Class, additionally, for our axial and equatorial position, your CH bonds must always be in your staggered position to adopt the most stable or more stable conformation. Okay, so again, let's compare and contrast our two different positions here, your equatorial and axial. Let's check, ha. Ayan, for our axial and equatorial, again, this is your equatorial. Ayan, and this is your axial conformation. It's in your axis. Okay, so the equatorial, class, it aligns in your equator of our ring plane or chair conformation plane. Okay, let's discuss. For position again, parallel to ring axis. For equatorial, that's around our ring's equator. So class, sideway for equatorial or up and down lang po for our axial position. And again, very clear, more stable si equatorial, less stable naman po si axial natin because of the steric strain for your axial position. Particularly, if you have now different substituents attached to your carbon atom. For your strain, particular for your axial, we have one free diaxial interaction. So if you have here an axial, okay, so again, sorry, your axial molecule here can be positioned also here or of course up of your chair conformation. And because of that, class, highly sterically hindered yan ha. For equatorial, we can minimize the steric strain that can be produced or can be induced through the bonding of your different substituents. That's why for the preference, ang equatorial favored by bulky substituents because they are far apart from each other. For your axial, ayan, less favored, ayaw po ng bulky substituents natin. Okay, so class, don't forget the ring flipping mechanism here in which your chair conformers can interconvert that can give rise to your equatorial and axial conformers. Again, the energy difference between these two is due to your steric strain. Purely steric strain, particularly 1,3 diaxial interactions. Monosubstituted cyclohexanes are more stable when your substituent is in the equatorial position. So class, I know the positioning of your equatorial and axial are confusing, diba? So again, it's confusing because of your chair conformers. So for easy visualization, let's check our, ayan, your conformers and our typical axial and equatorial position. Again, for our visualization here, your axial are always up and down. So this is colored in red in our ball and stick and in our chair conformation. All right, for our equatorial, ayan, class, colored in blue, as you can see, it's sideways. It's in your equator, similar with our chair conformation. Okay, so class, again, for your interconversion, we can actually do ring flipping via our interconversion of your chair conformation. So let's watch this short animation. So class, this is rather a complicated process because firstly, your chair conformers will first adopt both conformations in its transition state. See, from your axial position, we translated or converted it to your equatorial position. Okay, class, again, we adopt first or temporarily your both conformation. Clear? Alright, so class, that's it for our discussion for our conformations ng alkane. And with that, we arrive at our last slide, our sample problem. Or you can pause the video in order to try answering our sample problem here. Or draw the chair conformations for the trans 1,4-dimethyl cyclohexane and then label the more stable conformation. Okay? Or you can pause the video, but for me, I will now discuss our answer here. Let's check. For trans, of course, this would adapt axial or equatorial position. Class, I know it's counterintuitive, but please remember that's a tip for trans. Okay, for your trans isomer, your position must be axial. See, they are trans to each other. They are far from each other. Similar with equatorial. As you can see, they are far from each other. Or between these two, axial, equatorial, which is more stable. So very obvious. The equatorial methyl substituent. Yes, that's correct. That's why we will label this as the more stable conformer. And of course, axial now will be the one that is less stable. Next. Arrange the following chair conformations in order of increasing stability. Class, again, please pause the video. For me, I will now discuss the answer. For our first conformer, this is your, again, axial, it's parallel. It is both up. Okay, they are both up for our methyl substituent. For letter B conformer, C, equatorial. And for C, as you can see, one is equatorial and one is axial. Or vice versa, axial, equatorial. Basta, one is equatorial and one is axial. Class, which is the least stable? Of course, that's your axial chair conformer because, as you can see, both of your methyl groups experience 1,3 diaxial interactions. Remember, that's literally our main steric strain source for your axial position. That's why it contains or it induces the highest steric strain. Clear? What's next, class? Is it the equatorial, choice B, or your axial equatorial? Remember, our source of steric strain is always the 1,3 diaxial strain. Let's correct or let's check our next, okay? Our medium, our chair conformer that has medium stability, that's your equatorial axial because one group experiences 1,3 diaxial strain. Class, again, always present po ang 1,3 diaxial strain if you have a 1 position or a substituent in your C1 position. And lastly, very obvious, your choice B, the chair conformer that has an equatorial positions will avoid the 1,3 diaxial interactions, thus it has the lowest steric strain. Okay, so class, that's it for our discussion on your alkenes. Alright, so as a summary, now let's have our final Lars words, your favorite slides. So let's check. Ayan, for the types, don't forget, we have 3, straight chain and branch. They are isomers, particularly constitutional or structural isomers. That's why they adopt the similar general formula, C sub n, H2 sub n plus 2. Okay? And thirdly, your cycloalkanes, remember class, we discussed this. It's general formula, C sub n, H2 sub n. And remember, we have angle strain for the formation of cycloalkanes. For instance, diba? For cyclopropane, it has 60 degrees. Cyclobutane, 90 degrees, and lastly, cyclopentane, 108 degrees. So it is deviated from our ideal 109.5 degrees for your tetrahedral, supposedly tetrahedral carbon. All right. Next, for the physical properties, again, as you increase your carbon chain, your state will change. For short chain, they exist as gas. For medium chain, they exist as liquids. And lastly, for your hydrocarbons, 18 carbons and above, ayan, they are solid in room temperature. All right. So for boiling point, don't forget this class. Again, the relationship, boiling point will increase as you increase the chain length, direct relationship. But it will be decreased if your if it will be increased, okay? If you have lower branching. Clear. For the melting point, remember, we don't have a general trend, but as you increase the symmetry of your hydrocarbons, ayan, your melting point will also increase. And lastly, don't forget the solubility, because hydrocarbons are nonpolar. Of course, they will be dissolved in their similar nature compounds and nonpolar solvents. So usually, class, these are also organic solvents, and relatively, they are water insoluble. Okay, last, ayan, for isomerism, we also discuss constitutional or structural isomers. Class, this one is again for your relationship ng boiling point with branching. Okay, for the reactions, we have three, remember, combustion, halogenation, and cracking. This is an industrial process. Firstly, for combustion, we have two types: complete when we have sufficient oxygen, incomplete when we have limited oxygen supplies. And here are the products inside the parentheses. Again, class, for complete, we mainly combust your alkanes completely. That's why we produce carbon dioxide and water as byproducts. For incomplete, on the other hand, this is harmful. Again, carbon monoxide, toxic gas, and soot or your carbon is, of course, a pollutant or environment pollutant. Clear? Secondly, for halogenation, don't forget, this is through radical substitution. And usually, class, we use chlorine and bromine in order to introduce halogen to our hydrocarbon to produce alkyl halide. So your radical substitution is due to the unreactivity nature of your alkanes. Diba? We discussed the three steps: initiation, propagation, and termination. And as we have seen, we formed radical intermediates. Remember that intermediates, it has one unpaired electron, and it's neutral class. And lastly, cracking again, breaking large alkanes into smaller useful alkanes. Okay, for sources, don't forget natural gas and petroleum, and they have specific uses. For fuels, of course, you are methane, propane, octane, MOP, diba? And for industrial uses, ayan, we have your majority of your hydrocarbons used as solvents in the lab, lubricants for engine, and for synthesis. Okay? Class, last, for our conformers, remember, this is particular for our alkenes because of the free rotation that occurs in your CC single bonds. Remember, these conformers interconvert rapidly. That's why we cannot isolate them in your solution. For our discussion, we use two different representation, Sawhorst and Newman, particularly Sawhorst angle view, your Newman viewed end on. So both of them are very important in our discussion of conformers. Class, recall, we have the specific angle between your front and back CH bonds in our Newman projection. Diba? We discussed, we have your 0 until 360 degrees, and we call that, again, your dihedral angle. Clear? For our cycloalkanes, remember our discussion of your chair conformation. Again, that's the most stable conformation for our cyclohexane compared to our boat conformation. So please recall it. Why is it the most stable? Class, because it has no angle rotation, no steric strain or torsional strain. Okay? So for our axial versus equatorial, remember, preferred ang equatorial because of its stability compared to your axial, particularly through the minimization or in order to minimize your 1P biaxial steric strain. So this is always present when you have a substituent at the C1 and C3 position. And finally, we have your ring flipping. Remember, this is the interconversion from your axial or equatorial or vice versa. And because of that, it actually affects the conformer stability. Okay, so class, that's it for our last words. So for our wrap-up session, we will now have our quick quest. Let's see. Please try answering our quick quest, ha? For our set of quick quest here, we will have your add one out question. So I will give you 4 different concepts. Determine which is the impostor. Let's see. First, methane. Second, propane. Third, ethene. And lastly, butane. Very obvious, diba? Of course, these 3, they are types of alkane, except this one. Sir, that's an alkene. It contains a double bond. Correct. That's why that's our impostor. Clear. Next, we have N-pentane, isopentane, neopentane. Sir, don't flash the last structure. Again, cyclopentane, obviously, this is the impostor. Your N-pentane, isopentane, and neopentane, actually, they are isomers. They are all acyclic. For cyclopentane, from the name itself, it's an example or a type of cycloalkane. Clear. Let's proceed with our next item. This is the reactions of your alkanes: combustion, halogenation, cracking. Well, sir, I think the last concept or process is the impostor. Check. Is that true? Yes, it's not a reaction of alkanes. And lastly, the physical or the properties or features of your alkane: tetrahedral geometry, saturated, double bonds, and nonpolar. Which is the impostor? Obviously, class, your double bonds. Remember, this is the characteristic of alkenes. Diba? For alkanes, we have your single bonds. That's why we have tetrahedral geometry for your carbon atom. And for your single bonds, again, we also dub it or call it as your saturated hydrocarbons. That's why they have relatively nonpolar CH single bonds. So I hope it's clear, ha? And lastly, we have our last item: Newman, Sawhorst, Fisher, and Chair. Class, this is our discussion on conformation. Which is the impostor? Of course, the Fisher. Diba? Remember, this is used in visualizing the chiral molecules, not for visualizing the alkane conformation. Alright, so I hope it's clear, class. Remember, Fisher for the is a visualization of your chiral centers. And with that, we are now done with our crash course 3. Diba, relatively shorter ang crash course 3. That's just about our alkanes functional group. And that means you are now going to answer practice test 3 about alkanes. Class, again, close your manuals when you are answering your practice test, and you can now review our discussions before answering your PT3. So for PT3, 10 items for 15 minutes. So that's it, class. So for our last crash course, under me, we will discuss our alkenes and alkynes for Crash Course 4. So that's it for this video. I will see you on our next video. Bye class, and please take some rest.